This presentation is about group 15 elements and their oxidation states. All group 15 elements have 5 valence electrons in the outermost shell, and thus they have an electron configuration of ns2 and p3 in their outer shell, where n is equal to the principal quantum number. The s orbital is full, but the p orbital is half full, which makes them stable in nature. These elements exhibit different oxidation states from -3 to +5, as we can see here with nitrogen, which can even form a very unstable +6. So let's focus on -3, +3, and +5. Because of the octet rule, these elements need to either gain or share electrons, giving them a -3 when gaining or +3 and +5 when sharing. It is common for these elements to be reduced by gaining 3 electrons, giving them the oxidation state of -3. This happens with metals, giving a binary compound with the Regeneron equation M3E2. An example is nitrogen reacting with calcium to give calcium nitrate and phosphorus to give calcium phosphide, and so on. However, as we move down the group, there is a transition from non-metals to metals through metalloid character. Not only is there an increase in metallic character, but also atomic size. As the electronegativity decreases, so does the stability of -3, and so the tendency to produce the -3 oxidation state decreases going down the group. And due to the inert pair effect, the oxidation state of +5 also decreases. Phosphorus and arsenic form very stable oxides in the +5 oxidation state. For example, here we can see it in phosphorus pentoxide and arsenic oxide. But as a covalent character decreases, we see bismuth only showing a +5 with fluorine, and that is due to fluorine having a high polarizing power. Meanwhile, the stability of +3 oxidation state increases as we go down the group. The elements in the group react with oxygen to produce oxide in the +3 state, like phosphorus trioxide and arsenious oxide. We can see trita-antimony hexoxide being amphoteric and bismuth 3 oxide behaving as a basic metallic oxide. The chemical properties of group 15 elements are determined by the oxidation states exhibited by them, so they display a wide range of physical and chemical properties. An application for a member of this group is the use of white phosphorus in matches. White phosphorus is highly reactive and spontaneously ignites around 30 degrees Celsius in air. So of course, white phosphorus is not randomly stored around air. Red phosphorus, which is stable at room temperature, is used on the surface of the box of matches. The red phosphorus can be converted to white by heat. The heat necessary for this reaction is created by the friction used when lighting a match. This heat causes a small amount of red phosphorus chain to be broken apart. Some of the phosphorus changes into white phosphorus, which spontaneously ignites by reacting with the air around to create even more heat, providing the starting heat in the lighting of a match.